Hello and welcome to the second lesson in Area of Study 2. Today we'll be taking a look at Flux and Lenz's law. We're going to take a look at magnetic flux, as I just mentioned, induced current, and therefore Faraday's law, as well as Lenz's law. So let's start off with a fairly straightforward and necessary question. What is flux? So flux can be thought of as the amount of magnetic field that passes through some sort of area. So in the diagrams below, I've pictured a rectangular loop, and in that rectangular loop, there is an amount of flux indicated by the arrows. And on the left, we have lots of arrows, meaning that we have, I guess, more flux, it's more dense. Whereas on the right, it's lower flux because there are a lot fewer arrows. We calculate it as the product of magnetic field strength and the area. And quite literally, the formula is therefore phi. That's the letter that's used to represent flux. So phi is equal to B times A, the magnetic field multiplied by the area. It's important to note that the area, when we talk about the amount of area for this calculation, we're talking about the area that's perpendicular to the field lines. So if, for example, the magnetic field was on an angle to the loop, then you would have to multiply that by something that you would find out by applying trigonometry to, and that would allow you to find the central perpendicular area or perpendicular magnetic field. And finally, it's measured in Webers. So first practice question. So that loop there with some magnetic field going through it, we're going to say that that magnetic field has a strength of 1.4 times 10 to the power of -4 Teslas. And that is perpendicular to the loop. The dimensions are 3.6 centimeters by 9.4. And I would like you to find the flux threading the loop. That's the terminology that we use. It's worth 2 marks. So you've got a couple of minutes to do the question, but it really shouldn't take you that long. All right, now that you've hopefully had a go at that question, what's the answer? Well, we apply literally what we just learnt. Phi is equal to the perpendicular area or the perpendicular magnetic field multiplied by the area. And we calculate the area because it's a rectangle, it's length times width. So it's 3.6 centimeters by 9.4 centimeters. Make sure that you always use the standard units, which is why it's 0.036 and 0.094. And you get 4.74 times 10 to the power of -7 Webers. That's the answer there. Mark allocation, you get 1 mark for the first 2 lines and 1 for the answer. Making it slightly more complex now, the same loop is rotated 45 degrees from the horizontal, as you can see there. I'd like you to now calculate the flux passing through the loop. Note that that strength of the magnetic field from the previous question, which is 1.4 times 10 to the power of -4 Teslas, doesn't change. Keep that in mind when you do this question, also worth 2 marks. All right, now that you've had a go at that question, what's the answer? Well, it's very, very similar in approach to the previous question, but with one slight change. And because we need to find that perpendicular value for either magnetic field or area, we have to multiply it by the cosine of 45 degrees, or 1 on root 2 or 2 root 2 on 2. There we go. So that's all the equivalent ways of calculating the value of flux. So you do that multiplied by the magnetic field, and again multiplied by the area again, calculating it the same way as you have before. If you wanted to, you could just use the area or even the whole value from the previous question. So you could almost skip that second step. And instead of writing 1.4 times 10 to the power of -4, you kind of just cross it out and write 4.74 multiplied by 10 to the -7. If you wanted, completely up to you. And of course, that ends up equaling to 3.35 times 10 to the -7 Webers. Practice question number 2. So this takes a little bit more thinking perhaps. So Jamie has a total of 60 centimeters of wire. So the maximum area given a perimeter occurs when the shape is a circle. So I want you to find the area of that circle that Jamie can make, assuming of course that they use all of the wire. Worth 2 marks again, so shouldn't take you any more than a couple of minutes. All right, now that you've had a go at that question, the answer is relatively straightforward, and this may bring back memories of other math subjects. The circumference of a circle is 2 pi r. Obviously, a standard of year 10 mathematics is assumed when you're doing physics, so make sure that you know all these relatively or quite basic things to do with geometry. So we equate our value of our circumference, make sure that it's in meters, so 0.6, and rearrange it to find the radius. Now we know the area of a circle is pi r squared, so we could pop that value in and we get 2.86 times 10 to the power of -2 meters squared. That's all for that question. So it's the use of 2 different formulas, so you get 1 mark for finding the radius from the circumference and then another mark for finding the area. These types of questions often come up in exams. You have to apply a certain scenario and potentially some knowledge outside of specifically the study design. So in this case, circles, but know a bit about them, and then calculating some things from them. And we'll see that in the next question. So Jamie then places the circle into a perpendicular magnetic field of strength 3.5 times 10 to the -3 Teslas, hence or otherwise, find the flux that threads the loop. It's only worth 1 mark, so it shouldn't take you any more than 1 minute. Now that you've had a go at that question, what's the answer? Well, we can use our phi equals to b times a. We know our a from the previous question, and we are given the magnetic field strength. So the 2.86 came from there, and our 3.5 comes from the magnetic field. If I wanted to make this slightly easier for you to read, I would have swapped these 2 values around, but same answer regardless. You get 1.0 times 10 to the power of -4 Webers. 1 mark just for the answer. Now we move on to something that is more complex, and you need to know kind of flux for this part and the rest of the lesson. So make sure that you've got that down pat before watching this part. So I've called this a bit of a prelude to Faraday's law. So I've got a diagram here with a metallic rod, and that metallic rod moves in the direction of V. Now there's a magnetic field, so the North Pole's kind of a bit closer to you and the South Pole's a bit further away. So the North Pole's the red one, the South Pole is the blue one. And as we move the rod in that direction, when you use the right-hand rule, you put your thumb going in the direction of the velocity, your fingers going the direction of the magnetic field, and you'd find that the force is upwards, which means that a positive charge will experience a force going in that direction. And that's really quite important to know for the rest of Faraday's law and then consequentially Lenz's law. So what does Faraday's law say? Well, it says that you can induce a voltage, that is, you can create a voltage by moving stuff. So essentially you're taking kinetic energy and you're transforming it somehow into electrical energy. And exactly in the situation before, so with this diagram, if that happened, you got an induced voltage that was represented by that formula there. So N, meaning the number of loops, multiplied by the change in flux over the change in time. Often we call this, we use the average of the induced voltage. And we often only consider the magnitude of it because the direction of the voltage will just give us a vector quantity. So most of the times you'll be asked to find the magnitude of the induced voltage. But otherwise, just keep in mind that the actual formula is this over here, whereas you'll most likely be using this. I will add one more thing, and that is the change in flux. So in a rod, there's no real indication of the area, the change in area. So there's a slightly different way that you can do this. However, that being said, the theory is all the same. So instead of the change in area, it's the change in the movement in one direction, which represents that change in area. So we'll have a look at an example, not specifically of a rod, but how that may work. I think we'll do that at the end of the lesson. So this is the mathematical basis. And this is what I mean by using the rod as opposed to, say, a loop. The concepts are, however, identical. So you don't really need to worry about this bit. This is purely so that you can understand why this is true. So we're going to start off with a formula that you will have learnt in area of study 1. So the force in what we consider to be DC motors on a side motor is NBIL. The number of turns multiplied by the magnetic field strength multiplied by current multiplied by the length of the relevant section. We're also going to use another formula, which is for work, and you may have learnt this in area of study 3, force times displacement. So we're going to combine those two formulas, and instead of using S, we're going to use X, because we're traveling in the direction of X, as you can see at the bottom over here. We're traveling in the direction of X, so we're going to use that instead of S. Now, I've capitalized N, doesn't really matter, lowercase n and uppercase n. In this case, don't make any difference whatsoever. It is just that in the formula, so when we go back here, you can see that it's typically indicated by an uppercase n, whereas in the other formula, it's a lowercase n. Again, no difference, so you don't have to really worry about. Now, what can we do? Well, we know that current is the charge with respect to time. So we can express that as the change in X, because that's what we're changing. The amount of charge within the rod actually stays the same. So we're changing X, and we're also changing it with respect to time. There's a bit of differential equations here. If you do methods or spec, you may be able to derive this yourself using calculus. However, don't need to, again, it's not really part of the study itself. We can then rearrange this question so that we end up with N, Q, and B on kind of one side, and we multiply that by length, so L, which is over here, delta X, because that's what we're changing, and delta T being the change in time. So we know that the area of the rectangle, I suppose, the way it moves, is L times X. So the change in area is going to be L, because L doesn't change, it's a constant, multiplied by the change in X, which means that we can simplify the equation slightly to be NQB multiplied by delta A all over the change in time. Now that's work. So we know that flux phi is B times A. So we can pop that in instead of the B and the A, because now it's just going to be the change in flux. And we also know that work from area of study 1 is QV, the charge multiplied by voltage. And because voltage is the same as the induced voltage, the units are identical, that means that we can put in, kind of divide both sides by Q, uppercase Q, lowercase q, they are the same thing. So again, don't worry about that. And you get the average change in induced voltage to be, well, the average induced voltage to be N multiplied by the change in flux over the change in time. So that's the proof, if you want to call it that. Again, you could extend this by considering vector quantities, and that will give you this value over here, the minus N. But again, this isn't, strictly speaking, part of the study design. It's purely for your understanding of how this whole thing works. As I mentioned before, questions will ask for magnitude. So usually the answer represented as a positive number is acceptable. It'll often specify when they want you to use a negative value. A bit more theory before we end off with a practical exercise. Lenz's law. Now, this is a particular aspect of the study design that is done often terribly, if I'm honest. A lot of people get things wrong here, and it's very, very easy to get it wrong because there are 4 different situations, and if you choose one over the other, you will get it wrong. So the important things to note is memorize these points. And they represent kind of these 4 over here. So the south pole heading away is going to be, and the north pole pointing towards the loop. So this one over here is going to be, so what is it? Our north pole is facing towards the loop, which means it is 1 or 3, and it's going away from the loop. So it's going to be 3. This one's going to be 3. Next one across over here, our north pole is now heading towards it, and it's already pointing at it. So that's going to be number 1. Now, in our bottom left here, we have the north pole facing away and heading away. So that's going to be number 2. And then obviously that one's going to be number 4. I have indicated here a solenoid, and we've considered this kind of this blue bit here to be this front bit of the solenoid, and the ring around it to be the coils. So it'll all make a little bit more sense once we get to the next slide, but those are the key points. The definition of Lenz's law is that the direction of the induced current in the loop is such that the magnetic field opposes the change in external flux. Now that sounds tricky, but when we put it into practice, I can guarantee you that it will make a lot more sense. So when we induce a magnetic flux, meaning we're moving a magnet either toward or away from it, as in literally moving this bar magnet to and fro and flipping around, that means that to oppose that induced flux, we need to generate an induced flux. And that induced flux comes from an induced current. And because of that, there's always going to be some kind of voltage generated, which is why I popped A and B here. So there's going to be some voltage between A and B. Now, with this understanding, it means that we can use magnets to generate electricity. We can move magnets back and forth, back and forth, back and forth. And you actually already know this because in DC motors, you have not the magnets moving, but something between the magnets moving. So that the principles are often the same. We're causing something to move due to the movement of magnets. So let's take a look at an example. So we're going to choose the one on the top left here. So this one over here. We have a magnet. The north pole is pointing towards loop, but it's heading away, which means that the flux is reducing in the direction of this blue arrow over here. Therefore, our induced magnetic flux opposes that change. So it wants to go in that direction, kind of out the loop and through to the other side. So that's going to be the direction of the induced magnetic flux. To get that from current, we apply our right-hand grip rule. So to get our induced flux going out of that loop, kind of away from us, so pretend that we are, say, between the North Pole and the solenoid. That means that we'll grip our fingers around so that they kind of point away from us, and we follow our thumb around and we find that the magnetic field, so the induced current, is going to be in the clockwise direction. That's a lot of theory, so we should probably do a bit of practice to finish it off. So square loop of side length 4 centimeters at 100 turns, passes through a uniform magnetic field of strength 8.4 times 10 to the negative 3 teslas. The loop initially starts so that the edge touching, so that its edge is touching the edge of the magnetic field, as shown. The loop moves at a constant velocity of 2 meters per second to the right. Find the magnitude of the induced voltage through the loop as it completely enters the field. 3 marks worth, and so it should take about 3 minutes. Hopefully you should be able to get this. There's a lot of information there, so make sure that you use everything that you learned from the start, all the formulas that you need to learn, and yeah, should be right. Well, now that you've had a go at that question, what's the answer? Well, a little bit of a longer process. We can use this formula, n equals to b multiplied by the change in A divided by the change in T. So we're just substituting the change in flux for B times the change in A. And we pop in all of our values. So it's a square loop, and that loop has side lengths of 4 centimeters. So that's the 0.04 squared. The magnetic field is there, 8.4 times 10 to the negative 3. The change in time, so the time it takes to travel 4 centimeters is 0.02 seconds at 2 meters per second. And the number of turns we have, is 100. So if you put that all into the formula, you get 6.7 times 10 to the power of negative 2 volts. Remember, the unit for induced voltage is still volts. Mark allocation, 1 mark for each of these lines. You have to have each of them. Of course, you can split it up into more, but at minimum, you have to have 3 lines. Now, sketch the graph of induced voltage over time as the moves into, through, and out of the field. This may take a bit of thinking, perhaps. How's it going to look? Maybe you're going to have to do some calculations, but after this, you should have a pretty good understanding of all the things that you need to do, or that you can do with induced voltage. Well, now that you've had a go at that question, and hopefully I haven't thrown you too far into the deep end by getting you to draw a graph, but it's going to look something like this. So as you calculated before, it was 6.7 times 10 to the power of negative 2 volts, and that lasts for 0.02 seconds. Now, then for a period of time, there's no changes, nothing happens, there's no change in flux, and then it eventually exits the field between 0.14 and 0.16 seconds. So provided that you had something that looks like this, or also a reflected graph in the x-axis, so you could start at this negative over here, go along here, and then finish up over there. That would also be fine, as long as you have those values there and you put the labels on your axes. For the 3 marks, you would have essentially 1 mark for each of those blue or red lines. Now we have a little bit of thinking to do for this question. So find the direction of the induced current when the coil is in each of the positions shown. So there's a blue, an orangey yellow, and a green. Okay, now that you've had a go at this rather interesting question, how do we do it? Well, this is going to be my thinking. You wouldn't have to write this all down. I would encourage you to do that, but you don't have to. In the position where it's blue, so we've got flux increasing out of the page. Induced flux opposes that change, so it increases into it, and therefore, by the right-hand grip rule, with the field into the page, the induced current is clockwise. You can see there's quite a clear process that I've gone through there. I've identified what the flux is, what's the actual change, how we oppose that change, and also applying the right-hand grip rule, what the direction of the induced current is within that loop. Now, orange one is going to be the easiest. Flux is not changing, so there's no induced current. Easiest mark you can get. And then finally, the green coil, we've got flux decreasing out of the page. So induced flux opposes that and it increases out of the page. So you can see there, essentially, you're decreasing into it / increasing out of the page. By the right-hand grip rule, the field out of the page, the induced current is anti-clockwise. So mark allocation, 1 mark for each, for the directions for each position. You don't have to write that all down, but I would certainly encourage you to, especially in practice, because this is kind of how you get quite good at doing Lenz's law. That is all for today's relatively theory-heavy lesson, I would say. We covered magnetic flux, induced current, Faraday's law and its mathematical background, and finally Lenz's law. Next lesson, we'll be taking a look at transformers and the application of flux. Quite an interesting lesson. There's always a question, or at least one, probably 2 questions at the end of your exam, and it's a very large chunk of this area of study, so tune in for that. Thank you very much for your attention. I hope that you found the lesson to be hopefully interesting and perhaps you learned something new. If you want to get in touch, you can head to airlearners.com and find me on the tutors page. My name's Noah Bajot. Thank you very much, and I will see you next time.